can we actually step back on the big field of stellar archeology? What is this process? Can you just speak to it again? You've been speaking to it, but what is this process of archeology in the cosmos?
Yeah, it's really fascinating. So I mentioned the lesser the mass of the star, the longer it lives.
Yes.
And again, for reference, for the next dinner party, the sun's lifetime is 10 billion years.
Mm-hmm.
So if you have a star that's 0.6 or 0.8 solar masses, then its lifetime is going to be 15 to 20 billion years. Nice. And that's an important range for our conversation because, again, if you assume that such a small star formed soon after the Big Bang, then it is still observable today. Mm-hmm. You mentioned old light before. Mm-hmm. Yeah, that light is like a few thousand years old, but compared to the age of these stars, it's nothing. Mm-hmm. So to me, that's young. It comes straight from our galaxy. It's not far. These stars are not far away. They're in our galaxy in the outskirts. They probably did not form in the galaxy mm-hmm. because, again, the hierarchical assembly of a Milky Way meant... Exactly. They formed in a little other galaxy in the vicinity, and at some point, the Milky Way ate that, which means it absorbed all the stars, including, these little old stars that are now in the outskirts of the Milky Way that I used to point my telescope to. Mm-hmm. So, what can we learn from these stars? Why should we study them? Now, these little stars are really, really efficient with their energy consumption. They are still burning, for the experts, just burning hydrogen to helium in their cores, and they have done so for the past 12, 13 billion years, however old they are. And they're going to keep doing that for another few billion years, same as the sun. The sun also just does hydrogen to helium burning and will continue that for a while, which means the outer parts of the star, well, pretty much actually most of the star, that gas doesn't talk to the core. So whatever composition that star has, in its outer layers is exactly the same as the gas composition from which the star formed, which means it has perfectly preserved that information from way back then all the way to today and going forward. So I'm a stellar archaeologist because I don't dig in the dirt to find remnants of past civilizations and whatnot. I dig for the old stars in the sky because they have preserved that information from this first billion years in their outer stellar atmosphere, which is what I'm observing with telescopes. So I'm getting the best look at the chemical composition early on that you could possibly wish for.
What kind of age are we talking about here? Are we talking about something that's close to that, like a 13 billion, 12, 13 billion age range?
That's what we think. Now, there's a small caveat here. We cannot accurately date these stars, but we use a trick to say, these stars must have formed as some of the earliest generations of stars, because we need to talk about the chemical evolution of the universe and the Milky Way for a second. So I already mentioned the pristineness of the universe after the Big Bang, right? Just hydrogen and helium. Then the first stars formed. They produced a sprinkle of heavier elements up to iron. Then the next generation of stars formed. That included, again, massive stars that they would explode again, but also the little ones that keep on living, right? So, and then the massive ones, again, explode as supernova. So they provide, again, another sprinkle of heavier elements. Mm-hmm. And so over time, all the elements in the periodic table have been built up. Mm-hmm. There have been other processes, for example, neutron star mergers and other exotic supernovae that have provided elements heavier than iron, all the way up to uranium from very early on. We're still trying to figure out those details, but I always say pretty much all the elements were done from like day 3.
So iron is where, once you get to iron, you got all the fun you need. Most of the fun.
Yes and no. I really like the heavier elements, gold, silver, platinum, that kind of stuff.
For personal reasons or for star formation?
Well, both.
I mean, like, what's the importance of these heavier metals in the evolution of the stars?
So they're the spice of life, right? So every supernova gives you elements up to iron. That's cool, but at some point it gets a little bit boring because that always works. But that's the baseline. We need that. And that's certainly what came out of the first stars, and then all the other supernova explosions that, followed with every generation. And it took about 1,000 generations, give or take, until the sun was made. So the sun formed from a gas cloud that was enriched by roughly 1,000 generations of supernova explosions. And that's why the sun has its chemical composition that it has, including, and somehow the planets were made from that as well.
So the supernova explosions, the many generations, are creating more and more complex elements.
No, it just goes all the way up to iron.
Yeah.
And then it's a little bit more of all of these elements.
Just more.
Yeah, it's one sprinkle, then another, and it just kind of adds up, right? Now, the heavy elements form in very different ways. They are not fusion made. They are made typically through neutron capture processes, but for that you need seed nuclei, ideally, iron or carbon or something. So the supernova-made elements are very good seed nuclei for other processes that then create heavy elements. And because they cannot be made everywhere, some of my stars have huge amounts of these heavy elements in them, and they tell us in much more detail something really interesting happened somewhere.
Well, wait, I thought the really old ones we would not have. So what does that mean if the old...
Yes, important clarification. So the stars that we are observing today, these old ones, they formed from the gas. And the question is, what enriched that gas? So it could have been just a first star dumping their elements into that gas all the way up to iron. And we have found some stars that we think are second-generation stars. So they formed from gas enriched by just one first star. That's super cool.
Yeah.
Then we find other old stars that have a much more complicated heavy element signature. And that means, okay, they're probably formed in a gas cloud that had a few things going on, such as maybe a first star, maybe another more normal supernova, and maybe some kind of special process like a neutron star merger that would make heavy elements. And so they created a local chemical signature from which the next generation star then formed. And that is what we're observing today. So all these old stars basically carry the signature from all these progenitor events. And it's our job then to unravel, okay, which processes and which events and how many, may have occurred in the early universe that led to exactly that signature that we observe 13 billion years later.
Is it possible to figure out like the number of generations that resulted in this, in these stars?
Well, we think we can sort of say, okay, this was like second generation or third, because the amounts of heavy elements in the stars that we observe is so tiny. One normal supernova explosion is actually already basically too much. It would give us too much of it. And the thing is, you can never take away things in the universe. You can only add. There's no cosmic vacuum cleaner going around sucking things away. The black holes are probably the closest to that, but they would have taken the whole star.
Yeah, they'd take the whole thing, not just...
They wouldn't take stuff out of the gas, So we have maybe 10 stars or so now where we are saying that they contain so little of these heavy elements that there must be second generation, because how else would you have made them? And again, I want to stress that the elements that we observe in these stars were not made by the stars themselves that we observe. That's just a reflection of the gas cloud. So we don't actually, I had to say that because I love stars. We don't, at the end of the day, we don't really care for the stars that we're observing. We care for the story that they're telling us about the early universe.
So the stars are kind of a small mirror into the early universe.
Yeah.
And so what are you detecting about those stars? Can you tell me about the process of archaeology here? Like what kind of data can we possibly get to tell the story about these heavy elements on the stars?
Yeah, it depends really on what star you find. There are many different chemical signatures. We actually pair up these days our element signatures with also kinematic information, how the star moves about the galaxy. That actually gives us clues as to where the star might have come from. Because again, all these old stars are in the galaxy, but they are not of the galaxy. That's a small but important distinction. So they all came from somewhere else.
So you can rewind back in time to kind of estimate where it came from.
Yeah. So we can't really say, oh, it came from that and that dwarf galaxy. But interestingly enough, so I just a few days ago, I submitted a paper with 3 women undergrads. It was so good to work together. And we found a sample of stars that have very, very low abundances in strontium and barium. So very heavy elements. And I had a hunch for a while that these stars would probably be some of the oldest because, as I said, heavy elements give you extra information about special events. And again, finding something that's really low means that must have happened either really early on or in a very special environment, right? Because we can only ever add. So if you find something that's incredibly low in terms of the abundance, maybe just one event contributed that max. So we looked at the kinematics. How are these stars moving? And they're all going the wrong way in the galaxy. How is that possible? Well, it is possible because now we come back to the protogalaxy. The protogalaxy was like a beehive. It just didn't really know what it was or what it wanted to become when it grew up. And it was absorbing all these little galaxies to grow fast. Some absorbed galaxies were thrown in going the main way, and some came in the wrong way. Happens.
Yeah, it happens.
But this could only happen early on when, there wasn't left and right and up and down. So stuff would come in from all ways. So now, 13 billion years later, we're
still doing it.
Yeah, they're still doing it. And B, we just looked for stars that have low strontium and barium abundances. And then we look at the kinematics, and lo and behold, they're all at hundreds of kilometers per second going the wrong way. It's like, dude, you must have come in really early on from somewhere else. So we call this retrograde motion. That's a clear sign of accretion. So something that has come into the galaxy. And because they're so fast, and it's really all of them, that must have happened early on, right? You can't throw a galaxy into the Milky Way right now the wrong way. It eventually will turn around.
Can you actually just, on a small tangent, speak to the 3 women undergrads? Like it's pretty cool that you were able to use a hunch to find this really cool little star. What's the process of like, especially with undergrads? I think that would be very interesting and inspiring to people.
Yes, it was a wonderful little collaboration that actually emerged in the fall. I really like working with undergrads and grad students, postdocs, and I came up with a new concept for a class at MIT where I wanted to integrate the research process into the classroom, because sometimes people find it really hard to email a professor, hey, I'm this and that person and I'm interested in your research. Could I possibly, come?
Yes.
And I wanted to streamline that and give and just trial how it would work to provide a sort of the safe confines of a classroom where you just sign up and do research in a very structured way. And I developed it. It was a lot of work, a little bit more than I thought, to map up an entire research project basically from scratch in 10 worksheets so that they could do it, again, in a very structured and organized fashion.
Oh, so you created this whole framework for them to do it.
The whole thing. But the promise was, you come sign up for my class, in teams of 2, you each get your own old star that has not been analyzed before. I don't know what the solution is because in research, we don't look up the solution at the end of the book. We do not know what we're going to find. Our job is to do the work and then to interpret the numbers, because our job as scientists is to find the story.
Yeah.
Anyone can crunch numbers. Anyone. It's kind of complicated sometimes, but it's
Yes.
doable, right?
Yes.
But coming up with a story, when you only have 3 puzzle pieces, what does a puzzle look like? That you have to be a little bit bold. You need to have some experience, and you need to kind of see the universe in 3D. You just need to kind of go for it. And that's the beautiful thing. I really love that.
And so this was a story of weird kinematics going the wrong way, combined with this particular weird signature in terms of the heavy elements.
Exactly.
And you have to come up with a story.
Yes.
About that.
And so the story of that paper is now, usually I don't say I find the oldest stars. When I talk to my research colleagues, I talk to them about we find the chemically most pristine stars, because that's actually what we measure, the chemical abundance that tells us, okay, it must have been 2nd or 3rd or 5th generation of stars, right? But these low strontium stars that go in the wrong way, like they're getting paid for it, they must be the oldest stars that came into the galaxy, because they formed before the galaxy was the Milky Way, right? And it's so cool, and it was so wonderful. So this class, it went so well in the fall. I had 9 people sign up. That's not unusual for a class, a specialty class at MIT, so small number. It was 8 women, and they were so into it that I said, okay, let's use this opportunity. You're going to do some extra work with me, and we're going to publish this.
Try to publish.
Yes.
I also like that you're using the terminology of chemically more pristine. When I'm talking to younger people, I'll just say that I'm more chemically pristine than them. I like that description of age. So there's this term of metal poor stars. So most of these old stars are going to be metal poor.
Yes, I search for the most metal poor stars.
And what does that, can we just define?
Yeah, what does that mean? I don't know who came up with this. I would love to know, but the universe is a complicated place. So many decades ago, someone clever came up with the idea to say, let's simplify things a little bit. Let's call hydrogen X, helium Y, and all the other elements combined metals, Z.
Okay.
When I give public talks, I always ask, is there a chemist in the audience? Let me just tell you, neon is a wonderful metal. And they're like, oh my God, what's he saying? But I'm an astronomer. I'm not a chemist, so I'll get away with it. So if you just roll with it for a moment, all the elements except hydrogen and helium are called metals. Now, if we look again at chemical, or the concept of chemical evolution, it means more and more of all the elements, everything heavier than hydrogen and helium, gets produced slowly but surely by different types of stars and events. So that's a monotonously increasing function. And so we look for the stars that have the least amounts of heavy elements in them, because that means we are going further and further back in this process, in that function, almost all the way to the very beginning. And that is the first stars, right? They started that process. That's why I said it was such an important transition phase, because we call the post Big Bang universe pristine, just hydrogen and helium, and after that the mess started. As soon as you add elements to it, things kind of get a little out of hand. That ends in this beautiful variety that we have everywhere these days.
Yeah, and you're looking at the very early days in the introduction of the variety.
Yes, exactly. When it was still a little bit more organizable. But the variety of different types of metal poor stars we have is stark. Many different types of stars, many patterns we have sort of identified, but there are still crazy ones out there that we're still trying to kind of fit in.
So what kind of stars have been discovered? So you've already a while ago helped discover the star HE 13272326. Great name.
Yes.
And HE 15230901. What can you say about these These stars and others that have been found.
I love them.
Okay,
They're my baby stars.
what do you call your baby stars? Is there
I'm probably the only
names?
one who can, spit out these names without cheating.
Are there nicknames? Are there nicknames?
Well, no, that's
it's not allowed.
Names.
Okay.
Right. Well, some colleagues at conferences have just called them Anna Star or Frebel Star because they didn't want to learn the phone number. I get
phone number. Yeah.
And these numbers are actually based on older sets of coordinates for these stars. So they, the minus in the middle means that they're in the southern hemisphere. So negative is in the southern hemisphere, positive is in the northern.
Got it.
And then 13 and 15 means they're sort of observable in the middle of the year.
Okay, so it's to do with the observation and where it was observed.
Yes,
and that kind of stuff.
Yes. But they have very different stars, both absolutely significant, career defining actually for me, but really pushed the envelope in very different ways. So HE 1327, the first one that you mentioned, that was the second generation star that we found.
Mm-hmm.
And usually people say like, oh, the first one is the big one and the rest is nobody cares. But to us, it proved that yes, we can do it. Mm-hmm. Because astronomers live in this sort of way of, there are a lot of serendipitous discoveries and that's really great. But we need to show that we can do it again.
Mm-hmm. Reliably.
Because then we're onto something. And it's not just some kind of weird quirk. And there are a lot of quirks in the universe. But we want to know, is that a real thing? Does that happen regularly? Is there something that we can learn? Right? Is that a piece of the story? Mm-hmm. And so finding the second one that was even a little bit more extreme than the first one really showed, yes, our search techniques work. We can find these stars. They provide an important part to the story in the sense that if we had more than 2 stars, and by now we have about 10-ish or so, what do they tell us about the nature of the very first stars? And what we found, again, working with the theorists, of course, who run these supernova models, is that, so actually, let me, before I get into this, these 2 stars had huge amounts of carbon relative to iron. So we usually use iron as a reference element for what we call the metallicity. So the overall metal content, the overall amount of heavy elements in it. Mm-hmm.
So that's why it's called iron deficient star.
That's right. So these stars are incredibly iron deficient, which means they must be of the second generation because there was, and interestingly enough, there was this discrepancy. A normal supernovae, until then, we thought would get us so much iron, and you would distribute that in the gas cloud, and then you would form this little star that we're observing. But the iron abundance that we measured was actually much lower than that. And I already mentioned, you can't take things away. That must mean these early massive POP3, we call them population 3, the first stars, they must have exploded in a different way than we previously thought. They can't output as much iron because they just can't. Otherwise, it wouldn't match our observations.
Got it.
And so that's when we started to work with several theory groups on supernova yields. So what comes out of
from the explosion of the supernova? Yes. That's cool. Supernova yields. And so this one was not yielding much iron.
Well, we needed to concoct a theoretical supernova that made less. Yeah. And it's actually surprisingly difficult because you can always add more in the universe, right? But you can't take stuff away. Mm-hmm. So Japanese colleagues kind of came up with the idea of a fainter supernova that just doesn't have enough oomph, when it explodes. So somehow there's less iron coming out. Mm-hmm. But at the same time, then these stars showed huge overabundances of carbon, 1,000 times more carbon. So how do you now get 1,000 times more carbon out of these poor first supernovae, right? Yeah. That was the theoretical challenge. And because we didn't have just 1 star, but 2, that really spurred the field to think about what was the nature of the first stars? How did they explode? What are the implications? Because if they are not as luminous and bright and energetic, that has consequences for for these early proto-galaxies in which, they must have been located in terms of, blowing the gas out, let's say, and disrupting the system. So much higher chance for the earlier system to stay intact for longer, right? So there's a whole tale of consequences. And this is what I mean with we need to find the story, because you do one thing and it's like the dominoes, there are consequences everywhere. And suddenly you have a different universe, right?
So what could possibly be a good explanation for something that yields a lot of carbon and doesn't yield a lot of iron?
Well, it's not so much an explanation, more like finding a mechanism for what happens in supernovae. And the official term, what was sort of, as I said, cooked up in order to explain the observations. And we have, by the way, found a whole bunch more of these stars, so that holds. And it's called a fallback mechanism. So actually, in the supernova, during the supernova explosion, a massive black hole emerges. And so some of the material falls back onto the black hole. Here is a vacuum cleaner now plopped into the middle, right?
Like a temporary one that just cleans up some of the elements?
Sort of, right? Because if you think of we haven't talked about this yet, but if you know what a star looks like, a massive star looks like in its interior before it explodes, you have hydrogen and helium still on the outskirts, and then you have heavier layers of heavier and heavier elements all the way up to iron. So you have an iron core in the center.
Yep.
And because you can't get any energy out of iron when you want to fuse to iron atoms anymore, right? That's when the supernova explodes, or occurs, really. It's actually an implosion first, and then you have a bounce of the sort of neutron star phase that occurs in the process, and then
that is
the
so
star
awesome.
gets disrupted. Yeah, it's like this giant basketball, and then it all goes out.
Implosion first, explosion after.
Yeah, and so in the process, right, if you make your black hole basically big enough, it will suck away some of the iron, because that's the closest in terms of the layers. You hold on to it. You don't let it escape. And carbon is much further out. You let it all go.
Nice.
And so
that explains why you can have a big oomph and not much iron yield.
Yes.
So is this explain the HE 1327?
Correct.
And others like it.
Yes. So it's very well established now that the lower the iron abundance of the stars are, the higher the carbon sort of gets. And carbon is such an interesting element in that regard. If we come back to the formation of the first low mass stars, right? So we had the hotter gas, just hydrogen and helium, that made the first stars. They were 100 solar masses or so, because the gas couldn't cool enough. So they were big and puffy. Carbon then, coming from the first stars, probably led to enough cooling in these gas clouds that enabled the formation of the first low mass stars. So think about what happened if there wouldn't have been any carbon, or the properties of the carbon atom would be different. It would not have cooled the gas in such significant ways, perhaps. There wouldn't be any low mass stars. We wouldn't be here today, right? And we're carbon-based, and so I think carbon is really the most important element in the universe for a variety of reasons, because it just enabled this whole evolution that we're now observing and literally seeing in the sky. And it's really fascinating.
So combined with the fact that you have the iron deficient, so all of that is probably important to creating humans.
Yeah. We need all the elements, but if you don't have stars, like the sun, small stars that can actually host planets that have long lifetimes, you need long lifetimes if you want to have a stable planet and develop humans.
So carbon is kind of important in many ways.
Yes.